Okay, YouTube, we're back. Here we go. Let's convert. Let's see, last time we converted to base 10. Let's convert from base 10. How do you do that? Well, sort of backwards, really. Here we go. All right, so let's convert from decimal to another base. Alrighty, how about this? Let's say I want the number 123 in base 10, and I want to know what that is as a binary representation. Okay. Alrighty, so we're going from places ones place, tens place, hundreds place, and digits 0 through 9 to placeholders ones place, twos place, fours place, eights place, 16s place, and digits 0 and 1. So this is what you do. Instead of multiplying like we did last time, take 123 and divide by the base going into. Now 2 goes into 123 61 times at most, remainder 1, integer-wise division, div and mod type of stuff. Right? So what is, now take the 61, div it by 2, you get 30, but the mod is 1, right? Do it again until you get 0 in your quotient. So 2 into 30 goes 15, remainder 0. Okay, and 2 into 15 goes 7, remainder 1, right? Because 2 times 7 is 14. And 2 into 7 goes 3, remainder 1. And 2 into 3, keep on going until you get 0 quotient. So the divisor is 3, the dividend is 2, the quotient is 1, and the remainder is 1, right? And then 2 into 1 goes 0, remainder is 1, right? Because, let's see, 2 times 0 plus 1 is 1. So the remainder has to be 1. And what do? You write those digits backwards. Those remainders are binary digits. When you divide by 2, the remainders are 0s and 1s. When you divide by 3, your remainders are 0s, 1s, and 2s, and so forth. So write these backwards, and I write them backwards because the last number represents the highest power of 2 that I divided by. So it's the highest order bit. 1, 1, 1, 1, 0, 1, 1. 1, 1, 1, 1, 0, 1, 1. So is that right? Let's see. 1 in the 1's place, a 1 in the 2's, no 4's, a 16, a 32, a 64, no wait, an 8, a 16, a 32, and a 64. So if we add up 64, a 32, a 16, an 8, a 2, and a 1, you get 10, 23, carry the 2, and 123. Yeah, that's right, check. There you go. So that's the algorithm for converting from decimal to another base. All right, take the same number and convert it to octal, base 8. When you divide by 8, the remainders are 0s through 7s, so those are the digits. Here we go. 123 in base 10 is what in base 8 or octal? So we're going from decimal to octal. So take 123 and divide by the base you're going into, and 8 goes into 12 once, remainder 4, bring down to 3, and 8 into 43 goes 5, so that's 40, so remainder is 3. And then 8 into 15 goes once, remainder 7, and 8 into 1 goes 0, remainder 1. So guess what the answer is? 173 octal. There you go. Okay, let's practice that up. Take the same number. It doesn't have to be the same number, but here we go. The same number, let's represent it in hexadecimal. 110, or decimal, equals what in hexadecimal. It's short for hexadecimal. I don't mean 6. I mean 16. All right, so take the number you're converting from base 10 and divide by the base you're going into. And 16 times 8 is too much, right? 6 times 8 is 48. 6 times 10 is 80. 80 and 48 is 128. Too much. So it's probably 7. 7 times 6 is 42. Carry the 4. 7 times 1 is 7 and 4 is 11. Subtract, you get 11. That's the remainder. Then 16 into 7 goes 0. Remainder 7. So guess what the answer is? 7B. Why? Because there are 16 digits in hex, 0 through 9, that's 10, and 6 more digits, A, B, C, D, E, F. But A means 10, B means 11, C means 12, C means 13, D means 14, and I did it wrong. Wait. A, B, C, D, E, F is 10, 11, 12, 13, 14, 15, like that. So 11, the remainder 11 is represented by the digit B. All right, nice. And let's see, does that work? Let's see. 11 ones and 7 16s. 7 times 16 is 112, plus 11 is 123. It does work. Good. Now, that's how you convert whole numbers from base 10 to another base. What if you're talking about, rational numbers? Let's try. Let's say I want 0.5 in base 10, and I want to convert it to base 2. You probably know the answer already, right? Let's see. Find out. Very simple. Take the 0.5 and multiply by the base you're going into, just the reverse. And keep this process going until you get a 0 after the decimal point, and then the 1 in front of the decimal point is the first digit after the decimal point in the binary representation. Now that makes sense because you got 5/10 on the left side and 1/2 on the right side. That's the half place, isn't it? All right, I'm starting with an easy example just to make this algorithm obvious. Okay, let's try it again. What's 0.25 from base 10 converted to base 2? Well, this should also be obvious, but here we go. 0.25 base we're going into is 0. All right? Now leave the 0 behind. 0.5 times 2 is 1.0. That's when you stop, when you get a 0. When you get a 0 there. Hang on. What just happened? Okay, so now write those digits. 0.01, the digits right here. Okay? 0.01. And that makes sense because it's a 0 in the 1/2 place, but it's a 1 in 1/4 place. So you have 1/4 equals, well, 0.25. That's right. All righty. That's good. What about this one? 0.375 in decimal is what in binary? Let's fill it in over here. Base 2. All right, so take 0.375, multiply by the base you're going into. That's going to be 0.75. Leave the 0 behind. 0.75 times 2 is 1.5. Leave the 1 behind. 0.5 2 is 1.0. That's when you stop, when you get a 0 there. And there's the digit, 0, 1, 1. A 1 in the quarters place, the 1 in the eighths place adds up to 3/8. Yeah, that's correct. What if we want to take that same number and convert it to a different base? How about hex? 0.375 in base 10 is what in base 16? Well, this isn't that bad because 0.375 is 3/8, right? If we multiply 3/8 by 16, it goes into 16 twice, and 2 into 3 is 6. So you get 6.0 already. That's when you stop, when you get the 0.0. And there's your answer, 0.6. 6/16. Remember, that's a 16th place in base 16, right? And 6 is to 3/8, which is 0.375. That's correct. Okay, sorry, technical glitch there. My audio went out. All right, now watch this one. This is crazy. If you take 0.123 times 16, you get 1.968. So the one's a digit in the answer, but the 968 tells me to not stop. Take the 968, multiply by 16, and you get 15.488. Leave the 15 behind and do 0.488 times 16, and you get 7.808. Okay, 7's a digit, 15's a digit, in other words, F. Leave the 7 behind. 0.808 times 16 is 12.928. Leave the 12 behind. 28 times 16 is 14.848. And I'm recording. Okay. Yeah, just a sec. Okay. And 848 times 16 is 13.568. All right, let's stop there. Look, when you hit a 0 in the decimal point, that's when you stop, right? We're not getting that. Or if the digits start repeating, what do we got here? We have 1, F, 7, C, E, D. They're not repeating. So you could stop if they're repeating, put a little bar on top, like 1/3 is going through repeating, right? So I could stop here and say, okay, it's 1, F, 7, and 12 is C, and 14 is E, and 13 is D, right? C, E, D. But it keeps on going. So I'm taking a rational number that terminates, and it's turning into a rational number that doesn't terminate. And maybe it repeats. Maybe it's even irrational. This is hinting at why we get round-off error. When we convert from one base to another, sometimes we lose information. Sometimes a terminating decimal becomes a repeating decimal. Or perhaps a repeating decimal becomes a terminating decimal. Or maybe a rational number becomes an irrational number. That's strange. Is that what's happening here? That's really strange. I didn't expect that. In any event, the types that we use in Java, double and int and so forth, they only have a certain amount of RAM allotted to save the digits, and you can only save so many digits. So we're going to lose some of these digits. That's a problem. Look, what if we keep on going? 0.568 times 16 is 9.088. I'm not rounding off. That's exact. 0.088 times 16 is 1.408. 0.408 times 16 is 6.528. 0.528 times 16, is 8.448. 0.448 times 16. That's not repeating, right? We had a 0.488 before. We didn't have a 448 before. If it did repeat, if we got a 0.488 now, we could just say it's going to repeat because the process would then give you 0.808 again and 0.928 again, and, right? Times 16 is 7.168. And one more. 0.168 times 16 is 2.688. So we get some more digits, and it's not repeating. Look, after the D, it's what? It's 916872, and it just keeps on going. It's a pattern here. It's not a repeating pattern, unless it's repeating after 20 digits or something, decimal place digits. So that is odd, isn't it? And take a look at this. Here's a true-false question for you. All right, hang on. Are you ready? Is 0.1 true-false? Is 0.1 in base 3 the same as 0.3 repeating in base 10? Is that a true statement? Well, 0.3 repeating in base 10 is 1/3, right? And isn't the first place after the decimal point in base 10, I'm sorry, base 3, the 1/3 place, and I have one of those? So that's a true statement. And there you go again. Converting from one base to another, we got a rational terminating decimal turned into a rational repeating decimal. That could be a problem. We're going to lose data when we go and convert back and forth between bases like that. That's a problem. Okay, that is good for converting from base 10. Let's leave it at that for now. Let's see. So let me minimize this. And let me say goodbye to YouTube. Bye, YouTube. Have a nice day.